Hello. Hi everybody. Good morning, and welcome to the first in a series of webinars where we're hoping to talk about testing GNSS devices and the sorts of things you need to do. If you move on to the next slide, Sophie. Sorry. So there we go. Slight technical hits. Today we're just going to slightly introduce ourselves. I assure you I won't do that on the other presentations. And Jeremy is going to have a little talk about Orolia, who we're working with on this. And then we're going to talk a bit about, why we should test GNSS devices, some sort of test methods. The agenda is slightly in the wrong order here, with test methods are next, and then some basic tests are after that. The idea is that we will build up as we go along with this series to get into more complex testing and more interesting methods. Okay, so if we move on to the next slide, Sophie. There we go. Right. Okay. Right. A very quick introduction to Heedra. So Heedra is a UK-based GNSS consultancy, really kind of specializing in testing GNSS devices. Sorry, we've moved on to now. I don't know whether that was timed or what. And we're based in Devon, and we look after the UK and occasionally do a little foray into Ireland. But we can help, we can support. If you're doing testing, if you need to understand testing you need to do, if you want people helping write test scripts. We do have, one of the guys is into, does RF electronics and particularly antennas. So we have some support for antenna designs. And we do some software work as well, particularly sort of technical software, so SDR work, also some FPGAs and things like that. LabVIEW, that kind of thing. Okay, so that's us. We've been established now just over 3 years, and really sort of just helping people out. And that's our idea. Okay. On to the next slide, Sophie, and I'll let Jeremy take over.
Yeah, thank you, Andy. Hello, good morning all, welcome. So I'm Jeremy Thomas. I'm the business manager for Orolia in Northern Europe. So I'm working closely with Andy and the Heedra team on GNSS simulation amongst a number of things. Really just a couple of slides from me today, a brief on Orolia and then another on core focuses and technologies. So I'll let Andy cover the simulation part, but there's a little bit more to Orolia as well. So Orolia as a group aims and in many ways is the leader in resilient position navigation and timing. So that's often known as PNT or RPNT. And while I'm based here in the UK, Orolia is predominantly French with our HQ in Les Ulis in Paris. We also have a US center in Washington. That supports much of our US-centric and government work. It's a necessity. And while Orolia was incorporated in 2006, our legacy goes back many years before that. But since 2006, we've grown fairly aggressively through 12 acquisitions. And many of you will be familiar with some of our brands. You've got things like Spectracom, McMurdo, Sabi on the beacon side, T4 Science, on the Masers, TalonX, and now Skydel, which forms part of the simulation side of things. So these are all now within the Orolia group. We've got a global presence, so we've got 9 facilities and an established local partner and VAR network, and this is where the Heedra link comes in. So beyond simulation, on the timing and space side, we've got Orolia Neuchâtel, so that's in Switzerland, and this specializes in our maser and oscillator frequency technologies. So just at a high level, so we time the Galileo and Navic GNSS constellations. So we do space maser clocks, timing constellations. And we also do timing for the respective ground segments as well, just to give you an example of how far we can take things. Then there are high-end frequency references and oscillators, so many of which are present in our embedded ranges of PNT systems, brands such as SecureSync and Versa, for example. And then in the US, on the facility side, there's our core PNT facility in Rochester, upstate New York, by the lakes there. And then in Canada, in Montreal, is the Skydell hub that hosts much of our simulation and SDX software development, which you will see in action today. So just coming to the end, maybe Sophie, the next slide, please. In essence, yes, we are a leading test company, but also a resilient PNT source company. So assisting mostly critical infrastructure. So we're talking communications, telecoms, broadcast, government and defense, things like radar, satcoms, and then into enterprise data centers, including things like financial systems, stock exchanges, you name it. And then mobile. So by the very nature of PNT sources, we are fundamental to mobile asset situational awareness. So here, anything from autonomous vehicles, UAVs, intelligent transport systems, cars, trucks, trains, ships, really anything that moves, we do the PNT part on that. So just to really finish up, while today's focus is on our good friends at Heedra and simulation, the key message here is we are a specialist in resilient PNT, which is protected through interference detection and mitigation technologies, IDM. So we also understand and minimize threats such as jamming and spoofing in an ever busy RF world. So I'll welcome your feedback and any conversations on this, and hand over to Andy for the rest of the webinar. Thank you.
Thank you, Jeremy. And there's Jeremy's contact details if you need him. So, okay, here, oops, there we go. If you want copies later, please do. Right, so just a quick view of me. This is me, the old guy there sitting in front of the simulator, well, actually in front of the screen. I've, let's say, started Heedra about 3 years ago, just over 3 years ago. Prior to that, I used to work in Spirent, and I was part of their simulator team there. I helped develop the original simulator as an engineer, and then in the last sort of 15 years or so of my time there, I was a sales guy for Asia. I retired from there at the end of 2016, and that's when I started doing Heedra. And my original idea was to help people with their testing. I found quite often people would buy simulators, didn't always really know what they wanted to do with them, or needed some support, and that wasn't always easy to get. So my original idea was to help with that. Over the time, I got involved with the Skydell guys and the Skydell software, and realized what a good thing it was and how good it was. So and then we've started supporting that and selling that in the UK territories. Okay, so if we move on to the next slide. So why should you test your GNSS devices? Why do you test them? Particularly if you're someone that's using a GPS device or a GNSS device in your product, why should you go and test it? What's the reason for testing it? Well, these things there isn't a one size fits all with GPS. There aren't just one device that does everything exactly how you want it. Accuracy doesn't necessarily mean quick and so on. So if you want really good accuracy, you probably have quite a slow startup receiver. If you want a fast receiver, then usually accuracy goes out the window, and different things like that. And depending on the environment you want to use it in, whether you want to use it in a sort of an urban environment where you've got blockages and multipath and all that kind of rich environment, or if you're using it on aircraft or a boat, or wherever you're going to use these things, using it for timing. So testing is quite important to understand that the device you're using is right, or the device you're developing is right for the application that you see it for. So if we move on the next slide, Sophie. So that's really what I've been saying. Understand the receiver meets its performance. So does it? You've got some requirements. Does it meet those requirements? Compare it with different receivers. So if you're making a product and you want to put a receiver in, does it meet the requirements? Does it do what you want? Quite often specifications aren't always 100% true, and it might say it does something, but then when you look into it, it doesn't do it quite the way you'd expect it to. Like in my time, I've seen receivers that say they're SBAS or WAS or whatever you want to call it receivers, but when you look into it, they track the SBAS satellites, but they don't use the data coming out of them to correct. So they're really only using them as another ranging source. They're not using them to get the data out of them to use that to help the position. So things like that, specifications aren't always completely clear to test things before you use them. You might want to evaluate a timing receiver just to see how good it is, or sorry, how quick it does a fix. And time to fix is something that people focus on, but is it necessary for your application? You can imagine if you're in a car in an underground car park, you come to the outside, you want to know fairly quickly if you need to turn left or right. So you need a fast fix for a car. But if you've got a receiver on a big ship that's sailing the oceans, it doesn't very often go through tunnels or places where it gets bad visibility. So it's basically on all the time. So it doesn't need to have a fast fix. Accuracy is probably more important for those receivers. So you want to see how well it acquires signals, how well it keeps track of them. What happens if it loses signals? How quickly does it come back when they come on? Say a car going through a tunnel or something. You may want to estimate the accuracy for position. You may not be interested in position. You may be interested in time. So you want to see the time accuracy. You may want to see how a receiver copes in an urban canyon when it only sees a few satellites, or satellites are all above you, all this kind of thing. And then maybe, later on when customers are using your device, they come back with problems. Maybe you want to be able to test those problems. If you've sold a receiver to someone who's, say, in Australia, and you're based here in the UK, do you want to travel down to Australia to test out to see if it's working? Not really. It's better just to have a device that allow you to create the environment or close to the environment they had, and find the problem and sort it out back here. So these are the sorts of things you can do with a GNSS test equipment. So if we move on to the next slide. Sorry. There we go. So sort of things that you might want to test are, is it tracking signals? How many signals can it track at the same time? I won't go through all of these. How does it cope with vibration? If there's short, sudden movements in the receiver, does that put noise on it? Does it cope very well with that? How quickly does it do a fix? How sensitive is it? How fast can you go and it still carry on? How quickly can you change direction and it cope? How quickly does it reacquire after you've changed direction? Many different things that you'd want to check. And as I say, a lot of those are really based around where you see this device being used, where you see it being, what the requirements are for its capability. If we move on again. So let's have a look at the different methods people use for testing. So if we go on to the next slide. So, first of all, you can use live sky, stick an antenna outside. You've got free signals. They're real signals. You've got no problems there. And, it's cheap. Antenna doesn't cost that much. But the problem is, if you see a problem, you can't repeat it. It's gone. It's a one-off event. The signals don't repeat. The satellites move. Everything changes. You've got no control. You can't set up. You can't block a satellite from one direction or another unless you actually go to a place and then maybe it's not blocked because it's not where you expect it to be. So you've got no control. So you can't make changes. You can't do incremental changes to see how things affect your receiver. You've got no truth data. You don't know exactly what's happening. You don't know exactly where you are, particularly if you're moving. And actually, if you're going to do a proper thorough test of a receiver, it can end up being very expensive to use live sky. Okay, for a quick kind of, is it seeing a signal test, but much more than that, it's not very good. So the next option, if we move on, Sophie. Is to use a simulator. So here you can get your first picture, I'm sure excited, of the Heedra simulator, which is system that we make here within Heedra, and then we use the Skydale software from Orolia as the basis for creating stuff. So the advantage with a simulator is you've got full control. You can set up the environments you want. You can set up the almanacs. You can set up satellite positions. You can introduce multipath. All these different factors that you would do. You've got full control over everything. You can do current signals. You can do future signals. When the signals are released, when new signals are defined. So at the moment now, L1C is starting to come out, but is your receiver going to work with L1C? Well, if you've got a simulator, you can try it out and see. You can readily interpret the results. They're there. You've got truth data. You know exactly where you're supposed to be simulating. You know exactly what satellites are in view. You know the geometry. You know everything. So it's very easy to see if your receiver's performing well or badly. And you can easily understand what affects your receiver. So, is bad geometry a thing that affects your receiver, or does it cope okay with that for a while? Does multipath affect your receiver again, or does it ignore it? Many things like that, how quickly it does a fix, and can you repeat that fix time and time again? All that sort of stuff makes it easy to really quantify and understand the capabilities of your receiver. It's repeatable, it's inherently repeatable, so you've got your tests, you can run them again and again, so you can check to see if things change while you're doing stuff. The disadvantages are that it's not real, so you don't know. You're relying heavily on the people that have made the simulator to make sure that it works properly, and that's one of the things that is important. And but other than that, it's pretty good. So, it has become the way that people usually test their receivers, particularly development of receivers. You need a simulator. So if we move on to the next one, Sophie. So the other method that's become more and more popular in some ways is to have a record playback device. As you can see here, we've got the Saphiron GDAS system here, which records signals and then replays them. The advantage of this is that you do get all the signals. So if there's noise in there and things like that, you get that. So you get a very realistic view. You can record real world environments and you can see how they affect things. It's relatively cost effective. It's repeatable because once you've recorded it, you can replay it again and again. But you've not got a lot of control over the system. You can't, for example, set up a constellation the way you want it to be. You can't specify the things like multipath or whatever. You get what you get, and it's not always easy to diagnose the signals that you've got. But mainly for things like testing how your receiver works in a particular environment. For example, if you testing the application, if you like, software that's running on your device, they can be very good for that. And particularly if you build up a set of test cases that you've used over the years, you can very easily see if things change. So it's good for a lot of testing. You don't get future signals. You don't have full control over things, but very useful as part of the test regime. Very complementary to a simulator. Okay, if we move on to the next screen. So just to summarize these things, so if you look at this live sky, it's not repeatable, it's not controllable, you've got no reference truth, no future signals, but it is real. It's okay for sort of basic testing, basic sort of go, no go, is it working kind of thing. A record playback, gives you repeatability. You've got some control over things such as power levels and things. Truth is harder. It's harder to get truth because the only way you can really see what the receiver's seeing, what it's seeing, is to put some receiver on there. So then you're only really seeing a receiver's interpretation, and you don't really have future signals, but it is real. It's definitely real. So it's very good, particularly good for application testing. It's also very good, used a lot for studying signals, understanding how what signals look like, and things like that. So it's very good for that. And then if you move on to simulation, if you're looking at a receiver and seeing how a receiver works, it's repeatable, so it's very good for testing again and again the same things. It's controllable. You do have the truth. You can do future signals, but the realism of it is only as good as the models that are in it. And the good thing about the Skydale product from Orolia is that it's well and truly tested. It's used in many places. So there's a good understanding about the models that are used and how well they perform. So it can be used very well for testing. And simulation is really about testing the performance of a receiver and how a receiver performs, particularly in different environments. Okay, if we move on to the next one, Sophie, sorry. So what do you test? How do you test with the simulator? So looking at it from a higher view, the simulator, you put in your parameters, what signals you want, what obscurations, what multipath, environment, all the environment, any errors, you can put errors on the satellites, you can put errors on the data, the environment conditions, atmosphere, things like that. Set the location, set up motion, all the things that, you can think of on a receiver. And all of those things are stored, if you like, in files. And then when you run the simulation, it generates that data and gives you an RF signal that you can use to put into your receiver to see it working. Okay, and having a known signal source with timestamp truth data, it's controllable, it's repeatable. That gives you, trusted, accurate, and measurable results. Okay, if we move on to the next slide. Okay, so another factor you need to think about is where you are when you're doing your testing. So in development, this is where you really need the high-end capabilities of a simulator. You're developing receivers. You need to, understand the characteristics that you require. You need to understand what you need it to do. It has to be repeatable. You need to be able to create complex scenarios, test cases, and you need a great deal of flexibility because that's what you're going to be doing. So you have that level, then you get into a level where people are integrating receivers, so they'll take a chipset or something and put it into their device, sort of like a phone or a handheld or something. And then, again, you want repeatability. You want, particularly, if you're changing it, you might change the chipset at some time. So you want to see that the new one's going to perform as well as the old one. You want some fixed tests that you run. Don't necessarily need to change them all the time, but when you're creating them in the first place, you probably do want to do some stuff. In manufacturing, you typically want something a little bit more simple, just a sort of go, no go kind of testing, testing maybe sensitivity, testing time to fix, something that's repeatable, something that can be measured easily so that you can, see how things change over time. And then there's a sort of an area where, pre-mission or calibration, you want to, annually check or pre a flight or pre a critical mission, do some, checks on the device to check that it's still functioning as it should do, check that, all the connections are made and stuff like that. So you have that kind of area as well. So if we move on, Sophie. Right, just to summarize where we were. So, a simulator lets you create the environment, it generates RF signals that will go into your receiver. Those signals meet the ICD, and then the receiver will generate a positional fix. You can at the same time take a positional fix from your simulator and compare positions. You can compare offline. So it's about stimulating receiver with a known signal. It needs to be stable. It needs to be repeatable. You need to have flexibility so you can change conditions, create new conditions. It's a very efficient way of doing things. and it's it's a complete, if you like, test set for GNSS receivers. So if we move on to the next slide. So what I'm going to look at now is the sort of measurements people tend to make on receivers. So when you're testing your receiver, what are you measuring so that you can see how well it does? So typically what you do is you create your tests and then you'll measure something, and it's the measurements that tell you how the receiver's performing. So if we move on to the next slide. So the characterization, the measurements that you would use. So typically time to first fix, this is TTFF. It's very commonly heard. It's not necessarily critical, but typically what you do is you obviously introduce a signal to the receiver. How quickly does it get a position fix? And how do you decide that it's got a good positional fix? So if you measure it's how inaccurate it is, if you like, and then tick a box once it's within a certain accuracy. You may then want to change conditions on that to see how they affect the time to fix. So you may want to put all the satellites above you, or all on the horizon, or whatever. Acquisition sensitivity. How low can a signal? How does the signal power affect the acquisition at startup? So the lower the power, the slower a receiver will be to lock on, and the slower it will be to get a fix. So you're checking how well it can acquire signals. Tracking sensitivity is looking at when it's got a signal, it's happy, it's tracking, and then you take the powers down. How does it cope then? What level does it drop off? Positional accuracy obviously is a good test. So how accurate is it? How accurate is time? How accurate is velocities and things like that? Signal acquisitions, reacquisition. So if it loses signal, say you've taken the power down, loses signal, when you bring it back up, when does it reacquire it? Or if you go into a tunnel and lose a signal, go back out. That's important for people that are maybe doing devices that go in cars or mobile phones. Possibly not so important in other areas. So it's understanding how those things affect you and what you might need to test. But at the bottom here, as it says, there's no universally agreed pass-fail tests or results. People write these specifications, and they can be economical with the truth sometimes. They will create their tests that are perfect for their receiver, and this isn't always right for you. And of course there's no golden receiver, if you like. No, this is the perfect receiver. They're all good at some things, they're not good at others, and that's what, by doing these measurements, it allows you to understand these things better. And required performance really that you need depends really on your application. So if we move on to the next slide. So I'm going to look a little bit more at each of these measurements. So time to first fix, it's commonly seen. You see it quite often on specifications. What does it really mean? Well, it's how quickly does a receiver get a fix when it first starts seeing signals. Really, you should start with a cold start. So your receiver should be cold, which basically means it doesn't know anything. It doesn't know time. It doesn't know a position. It doesn't know the almanac. And then you apply a signal. How quickly does it get a fix? And then how quickly does it get a fix within a required accuracy? And this is the thing that's sometimes overlooked. I've seen people that are doing a TTFF fix, and they just, it's ticked the box to say it's got a fix, but actually that box might just say it's tracking 4 satellites, and it still could be hundreds of meters out on position. So that isn't really a first fix, or it isn't a good fix. So it's important to check the accuracy. Typically as well with these things, receivers aren't always fully cold. They do remember things. If a receiver knows time, it can speed up its acquisition quite a lot. If it knows the almanac, it will speed up a lot. If it knows roughly where it is within, say, 100 meters or so, or even a few kilometers, it will really help to speed up its fix time. So it's important to maybe run a series of tests and not only cold start the receiver, but also change the almanac, change the time, change the position between each test. So then the receiver really is doing a cold start each time, and then you can get a real measure of its first fix. And generally, you'd probably want to build up a statistical view. So maybe do the tests a number of times, and then understand statistically, how it's doing. But so time to first fix sounds an easy sort of measurement. There's a bit to think about behind it. And then when you move forward and you'll start looking at, your particular receiver, well, if you're in a nice, clear, open space, your fix time might be quite good. If you're in an urban canyon or next to a building, or you block signals to the south or something like that, then your fix time might not be so good. And it's understanding those sort of things as well could be useful for your requirements. If we move on to the next slide. So the second measurement is acquisition sensitivity. At what power level? So GPS signals are very low power. About minus 130 dBm is the minimum received power at ground level from GPS. And that's about a trillionth of a watt, to put it in context. So it's a very weak signal, and yet people, want to be able to track or get their receivers to work at even lower powers. So what's the required sensitivity for your receiver? As I say, if you were going to put your receiver on a boat, for example, at sea, it's always got a clear view of sky. It shouldn't really see signals that low. Minus 130 should be what it should expect to receive. But maybe you want to check it a bit lower just to give you some measure of confidence that it will work going forwards. But what level do you want to check at? A phone receiver, for example, may need someone switches it on when they're in an urban canyon, or maybe even under an awning or something like that, and they want to get a position fix. So sensitivity is much more important for that. But a phone is attached to a network and it gets assistance data, and that can help it with its sensitivity. So all these things need to be taken into effect. But again, cold start, so that the receiver's clear. Start the scenario, start the signals, at low power, very low power, and then bring them up until it starts to acquire. And then once you've got that sort of acquisition point, and then try and see how, try the tests again with the signals at that level, and see how quickly it will acquire a signal, and go from there. Typically, you find that when they go down, it will take longer to acquire. You will also typically find that if you're doing a positional fix, the fix won't be as good. That's the way it goes. If we move on to the next slide, Sophie. So tracking sensitivity. So if you are already got a signal and then you're tracking it, how well does it work? So what's the minimum power level where the receiver can keep tracking? And again, accuracy will come into this as the signal power goes down. So the accuracy will degrade, and at what point is the accuracy not good enough for your requirement, and checking the sensitivity. Quite often with sensitivity as well, you may want to see what happens when you've got a high power receiver. So you're seeing some satellite clear to the sky, and then the other ones are coming through foliage, say, if you're in a woods or something, or something that's causing the signal power to go down. How well do they cope then? Is there a limit between the power levels of the high power signals? Does the receiver have a sort of a range on its front end where it starts to drop the lower power signals just simply because there's a high power sort of flooding them out? Many things you might want to check on a receiver, and these are the areas where we can help you understand these things. If you move on to the next slide, Sophie. So obviously accuracy, how accurate is your receiver? How accurate, and I put position accuracy here, but really I should have put just accuracy, because time is important for a lot of people as well. As Jeremy said, as Orolia does with their timing receivers, time accuracy is very critical. Is it maybe just a 1 PPS? How good is the 1 PPS lined up with GPS time? But how good is time accuracy and time stability. Time is a big application for GNSS these days, and many devices are having time can be quite critical, and if time drifts, then things don't work so well. Things like mobile phone networks, the 5G now is supposed to be, I think, 30 nanoseconds accuracy. Well, you're only going to do that if you're tracking GNSS signals to keep the accuracy up. So these are the sort of things that you need to worry about. 30 nanoseconds, light will travel about 10 meters. So it's quite critical to get that sort of accuracy. If we move forwards, number 5 is reacquisition. So, for example, you can see they're going into a tunnel, or somehow you've lost the signal. Maybe you've been jammed. These jammers are around these days. It's personal privacy devices, and they cut your signal off. How quickly does it reacquire? How good is it when it reacquires? What happens if you're trying to reacquire in a poor visibility area? Many things like that. Lots of things to test to see how good your receiver copes when it's reacquiring signals. Okay, so if we move on again. So an overview of the testing then. So, GNSS testing basically requires stimulating the receiver with a real or realistic signal. The signal itself should be stable. It definitely needs to be repeatable. It's very important to be repeatable. And the receiver output data should be compared to truth data. So, how accurate is it? How good is it? That sort of thing. This really performs the basis of GNSS testing. Following on, once you've got the basic test there, then you need to start adding events or adding effects to see how that affects your receiver. So things like leap seconds, atmospheric effects, things like scintillation or bad atmosphere, sun activity causing heating of the atmosphere, day-night effects, things like that. Maybe there's some errors in the nav data, or the nav data is not being received properly, and so you've got some parity errors. Does it cope with that? Geometry of the satellites, or what's known as DOP, dilution of precision, how that affects it. And normal operating conditions and extreme conditions sort of thing. So if you're looking at, say, a receiver that goes on a car, well, do you test it at 200 kilometers an hour? Do you test it at 500 kilometers an hour? You're probably not going to be driving a car at 500 kilometers an hour. Some people might be driving at 200, depending on the car they've got. So, what's your measure of measurement, and what's your sort of level of, comfort, if you like. Obviously you need to go beyond the sort of expected operation, but how much beyond that do you do? So, you control conditions, you check how it does. You may have additional sensors, and they need to be on, so you may be trying to simulate inertial at the same time. Dead reckoning, sort of wheel ticks, compasses, gyros, that sort of stuff. Altimeters, that sort of stuff. You may want to model those things at the same time, and you can apply those effects, externally. And other external effects, interference, it's a big thing these days. Spoofing is a big thing these days. It's a particular type of interference which can be quite nasty. Solar activity, sunspots will affect the upper atmosphere, will affect the delay of the signal, will increase the delay of the signal coming to you, can put things out. I did hear of a timing receiver. I don't know how good this was, but I did hear of a timing receiver getting moved more than 100 nanoseconds out of lock by sunspot activity when there was a solar maximus. So, that's 30 meters of error, if you like, on position, purely from heating up of the atmosphere. So, it's something to look at. And of course, at night, there's virtually no heating of the atmosphere, so you have much less effect. Multipath obviously can cause effects, and and how that affects your receiver, how it it tends to drop out the peak of the signal, so it makes it harder for the receiver to lock on. But the important thing about when you're testing is, you incrementally build your test. So you start with a clear, easy test, something that gives you good conditions, everything, and then you incrementally apply conditions. So you start to add maybe multipath, see how that affects your receiver, then take the multipath off, and then maybe start to change atmosphere, see how that affects your receiver, and then take that off. And then, build up, more complex tests by adding multipath and atmosphere or whatever. But it helps you to understand where your receiver drops out, what are the problems that affect your receiver. Okay. So if we move on again, I think I've got to try and be clever here. And yeah, so I'm going to try and run the Skydale software from my PC now, and see how that works. It may or may not, but we'll see. So can people see my screen now?
I was going to say, Andy, it looks just like the slide.
Oh, right.
Yes, I see.
Okay, you've got the Skydale software up. So so this is just I'm just going to do a very quick demo here of the software. I'm not going to go into any great detail. Next week, if people come back, I'm going to start going into showing you how to do incremental testing, how to make changes to the software, and that will be much more interactive. So this week, so first of all, we have to decide the output. So we have to add an output signal. So we select the signals we want. So if we look at upper band, maybe GPS, maybe GLONASS, maybe Galileo, maybe SBAS, and then we'll say that. So now, if you're looking at my screen, you can see in the bottom here we have.
Andy, I don't think you shared your screen properly, actually.
No? Oh, right. Okay. Let's click again.
Yeah, I can only see the slide. Okay.
Let's try this. How's that?
Better.
Better. There we go.
Hey. So I start again. Sorry. I'll start again. Okay, so I've cleared it now. So we'll start again. So first of all, we need to output signals. So we need a way of outputting signals. So we'll add some signals. Let's have, you can see here, GPS upper band. We'll put it on the GPS. We'll put on GLONASS, Galileo, maybe a bit of Gaussian noise, maybe some SBAS, and we'll say okay to that. So say now, down in the bottom here, you can see the sky plot now has added a lot of the constellation signals. If I want to add lower band, for example, so GPS L2, L5, Galileo, all the Galileo E5 signals, and then click OK on that. It won't change the sky plot because it's the same satellites. We may want to change time, so if we put, let's put nearer to today. Click OK on that, so that's this Sunday coming up, and you can see sky plot moved here. And we may want to put a vehicle position, so let's, I'll do a fixed vehicle, but we'll put it somewhere in the middle of the UK. Somewhere around about Oxford, if I've got that right. I can zoom in on that, by the way, to make sure. So yeah, it's pretty close to Oxford. Use that. And then say OK. And then you can see we've got our where we are. And then you may want to play with the antenna, edit the antenna pattern. I won't do that now. And then and then we can start running. So if we press start, now the scenario is running. The receiver position is shown here. It's a bit slow to come up, I'm afraid. Spectrums here, you can see the spectrums. And sorry, not receiver map. Spectrums here, you can see we've got the L1 band here, you've got GLONASS here, you've got all the other signals, GPS, Galileo here. And then on here, you've got the L5 signals and the L2 here, GPS. So you can see the signals being generated. You can see the constellations here. Maybe you want to play with this a little bit. You can change power levels. Maybe you want to add a reflection of one of the satellites. So I can put some consider range offset on there. Maybe some power loss. And put that on. So you'll see, if you do a summary, you see now I've got one reflected satellite there. Don't really see too much here. And there we go. That's a very simple. So that now is generating signals. Your receiver could be plugged in, and seeing, and if you should be able to get a position of the receiver. Oh, okay. Right. So I think if I stop sharing now and go back to the slides. Okay, the slide's up now. There we go. So that's that. So if we move on to I think more or less the last slide. There we go. So we're going to try and run this next week, same time, same place, where we're going to have a go at tailoring the test. So you can, as I was talking about, this incremental changes to show you how you can do that, and show you how you can save that. So you've got a repeatable control test. And then 2 weeks' time, we're going to start looking at more robust PNT. So how good a receiver is, how resilient it is against noise, jamming, multipath, all those kind of things. Look at maybe at SERPAs, particular antennas, and other advanced requirements. And then at the moment it's still in planning, but maybe the week later, July the 9th, we'll be looking at some record playback systems and doing a look at that. Okay, so if I think the last slide now, Sophie, is just my contact details. That's right. So if anyone wants to take this any further, please feel free to get in touch. There's my contact details. I'm based in the UK, so I'm on British summertime at the moment, so we're an hour offset from Europe. But feel free to get in touch, or email me, or whatever you want to do. Okay. Is there any questions then? Sophie manage the questions, and we'll see what we can do.
Excuse me, Andrew, here is Yuval or Flavio from Safirion. Among the possible issues in record and playback, you mentioned that the future signal are not immediately made available. Now, I wanted to ask you, what are the future signal you are thinking about? Because in the GNSS domain, already implemented, there is the S-band signal of the Indian Navik constellation. After that, there are some rumors about possible future developments in also other constellation, but not so many. Now, are you thinking just of a new signal for GNSS, or also opportunity signal like Wi-Fi networks, something like that?
Well, everything really. I mean, the GPS constellations are not standing still, and they're being modernized. There's talk of Galileo modernization. There's, L1C is a new signal on GPS coming up, and it's not on, I think it might only be on 1 or 2 satellites at the moment. So if you want to see how your receiver performs, when these new signals come out, they'll be on a receiver quite early on. Whereas, if you want to test them on the live sky, you can't test them until they're actually on the satellites. And if you want to have them with a full constellation, that can be some years after the first signals come out. So for checking that sort of future proofing, if you like, it gives you an opportunity to do that. But a lot of the signals, I mean, they do come online fairly quickly, but usually there's a year or two's delay between the signals being specified. And I guess a few years ago, and you have to excuse me, I'm a bit old, so I remember these things, but a few years ago, when Galileo was being developed and GPS L2C and L5 and all that were being developed, the specifications for those came out some time before the satellites were produced and were active. So there's, there is a sort of, it gives you an opportunity to get your receiver ready for these new signals before they appear in the real world. Okay.
Oh, okay, thanks. That's a good point.
Yeah. But you're right. There isn't so many new signals coming out now as there were.
No, because I was thinking that if I remember correctly, I am a laser engineer. I am not totally aware of all the nuance of this world. I have heard that, for instance, there is a new Wi-Fi standard that could allow, if I remember correctly, some direction of arrival measurement, and therefore could provide in constrained environments like urban canyons some extra signals that could be integrated with GNSS in order to provide a better positioning. So my curiosity was to understand if, in your expert view, you see an arrival of new signal, but still in the domain of orthodox, let's say GNSS signal based on satellites, which broadcast them to the Earth, or you have some feelings that some other terrestrial-based positioning system could be phased in very quickly.
For sure, there are, there are. I mean, positioning is a big thing at the moment, and if you look at GPS when it came out and started being used heavily, it transformed navigation really from where we were. You could have, very accurate navigation almost everywhere, but the sort of 10 meters or so accuracy of GPS isn't good enough now. People want better, but it's very hard to get GNSS signals to the accuracies that you would need for autonomous vehicles and things like that. So, people are changing. There are new signals coming out of that, and there are developments going on for ground-based navigation, as you say, Wi-Fi. They're talking about 5G and all these kind of things, which will hopefully, could give you better navigation or could improve your navigation, if you like, for those applications. But those things, I wasn't really thinking about those. I was thinking more about the GNSS signals.
Okay, thanks.
Andy, perhaps in maybe the next session or something, we take a look at the 2020-2021 roadmap for there's quite a lot coming up and in development that will probably be quite exciting.
Yeah, we can do that.
Great.
Okay. Any other questions out there? Anybody? Obviously you can contact us later. Feel free to get in touch if you've got any other questions that you feel need to be covered. As I say, hopefully people will come along next week. We're getting into more detail next week and getting more into how receivers can be tested and how useful they'll be, if you like. So feel free to do that. Okay.
Okay, thanks a lot, therefore, and hear from you next week.
Okay, all right. Okay, thank you very much.
Goodbye to everybody. Goodbye.
Thank you. Bye-bye.
Thank you. Goodbye.
Yeah.
Cheers, Andy.
Cheers. Cheers.